Oh yes.
I'm scared.
The number 12.
The number 12 is a number we can find in any culture.
Row.
12,
12. That was that.
wow.
9 o'clock, 10 o'clock, 11 o'clock, 12 o'clock.
If I see 12, I'm doing 12.
12 is 12.
11, 12.
BC Calculus students, it is with great excitement that today we start Chapter 12, our last full chapter together, and what a crazy and wild and fascinating chapter it is. So first I present you with this thought. When I tell you to multiply 7 times 7, you know it's 49. It's pretty easy to multiply numbers together, right? You get 49. But when I ask you to take the square root of 50, let's say, how do you go backwards and tell me the irrational number 7 point something that multiplies by itself to create the 50? That's a lot harder to comprehend. Well, Mr. Wade, I type it into a calculator. Well, how do you know the calculator's right? Somebody had to correctly program that calculator. But how do we grapple with taking the square root of things that are not perfect squares, right? I mean, the intro to this whole entire section right here is so fascinating and so deep. I feel like I should do it as a TED Talk. If you've ever watched some of those, they're absolutely fascinating, all right? I mean, this is just such deep thinking. You know what? As a matter of fact, I've always wished that I could do a TED Talk. I want to be on the stage entertaining people with intellectual ideas, you know? I wish I could teach this lesson as a TED Talk. Thank you. So I ask you, what is the square root of 9? We all know the square root of 9 is 3, but what makes that happen? Because 3 times 3 gets us back to 9. Now wrap your heads around the square root of 10. What is the square root of 10? Well, it's 3 point something. It's an irrational number that goes on forever with no pattern. But try to find that number that is irrational and multiplies times itself to get you exactly back to 10.0 repeating. It's very difficult to ascertain. It's very hard for the human brain to wrap around that. Now think about sine. So this is where it becomes exceedingly difficult when you think about trigonometric functions. Think about the sine of pi over 2. We all know that pi over 2 is 90 degrees. And 90 degrees is its degrees form, but pi over 2 is its radians form. Pi over 2 is roughly 1.571. That's the radians version of 90 degrees. When you say find the sine of 90 degrees, pi over 2, we all know it's 1 because it's a peak on the sine graph. They knew that back in 150 BC. That's how long we've known that. Long before calculators. But now try to wrap your head around the sine of 84 degrees. Okay, well, 84 degrees is close to 90. It's close to the peak. But what is that pinnacle? Or how far does it rise at the sine of 84? Well, now we have graphs thanks to Pierre Fermat, but we didn't have that back then. So the sine of 84 degrees is about 0.99452. But how? How do we know that? How do we know how high that is or how close to the peak it is? We didn't know that until 1715. But how in the world did people know that in 1715 when, consider this, the calculator had not been invented yet? So mathematicians were busily at work trying to find, how do we represent the sine of 84 degrees? How do we represent the square root of 10? How do we figure this stuff out? Not even dreaming that there would be calculators someday, but maybe their mathematics would pay off and they would actually have a calculating device that people could hold in their hands that would do all this stuff for them. Pretty amazing, right? In 1972, the Hewlett-Packard 35 was the very first calculator in world history to contain sine, cosine, and tangent buttons. But wait a minute. Again, how did mathematicians know what the sine of 84 was, since it's not a nice 90 degrees or 180 degrees? And the better question is, how did they program the calculator so that when you touch sine of 84, it spits back out the correct answer? We just take it for granted. But how did the calculator do that? And how did they program it to do that? Well, let's take a little journey back to the classroom so we can see how we define all these unusual, irrational situations in our modern society then change does forever. Oh, sorry, I was fantasizing that I was giving a TED Talk. One thing I really want to do in my lifetime. Anyway, so, but as the guy said on stage, right, the sine of pi over 2 is 1. And the sine of 84 is almost 1, because where's 84? 84 is like over here at a peak. Matter of fact, let's add it over here. So let's see. Pi over 2, 90 degrees, peak. 84 degrees, probably like right about there. Let's say that's 84 degrees. Of course, these are all in radians right here. So the sine of 84 is almost the peak, 0.99452, right? Okay. So again, if the calculator that first debuted sine, cosine, tangent didn't come out until 1972, how did any of us know what some of these unusual sines or square roots or cube roots or things were before that time? And how did somebody actually program the calculator, right? Okay, well, let me show you a few steps. You're going to be able to do it yourself in this chapter. You're going to become a human calculator. Are you ready for this? All right, step 1. Y equals sine of x should be written not as a trig function, because again, you know, coming up with the sine of 84 is just weird for our brains. We don't know what to do with it. You change sine into a polynomial. Wait a minute. How do you do that? I'm going to show you how to change trig functions and logarithmic functions and square roots and cube roots and all the rest of them into polynomials. Because we can handle polynomials. Polynomials are just x, x to the second, x to the third, x to the fourth. We know how to cube things. We know how to take things to the fifth power. We can handle that because it's just multiplying over and over again. We know how to divide, okay? So, y equals capital P sub 7 of x is going to be x minus x cubed over 3 factorial. That's 3 times 2 times 1, right? Plus x to the 5th over 5 factorial. Minus x to the 7th over 7 factorial. We're going to stop right there. This polynomial is approximately the sine of x for a while until it kind of gets to weirder outcomes. But for a while it works. How in the world did I just write a polynomial that would actually model the sine graph? That's pretty crazy, you must admit. Well, I'm going to teach you how to do that, okay? The capital P stands for polynomial. So we'll be using that a lot in this chapter. So you can make a little note to yourself there. Polynomial. And the sub number, the sub 7, stands for the highest power in your polynomial, okay? So that is the highest power or exponent, however you want to say that. All right, so let's sketch it, and we're going to mark the center up here. Watch this. Okay, first of all polynomials at their heart are either a parabola or a snake. They're either U-shape or they're one of these things, aren't they? Now, of course, they get more wiggles and curves in them the more powers you put in, but isn't the strongest power x to the 7th? So in its core, it's really a snake, but it's a negative x to the 7th. So it's really a backwards upside down snake. This is why I told you to know your graphs, right? So you can think about things like this. Now, when you put in a 5th and a 3rd and an x to the 1st, that puts more bends and curves, all right? So here's what happens. Imagine this snake reversed. Imagine it with a few more bends and curves in it, and I want to sketch it on top of the sine graph. You can even go to Desmos.com and sketch both at the same time. It's crazy. You ready for this? Let's draw an arrow, and I want you to draw right down into this graph, and I'm going to show you how closely it actually matches the graph, all right? So, let's see, actually, maybe a little bit lighter color. Let's do a blue. Okay, so this thing comes down, and it almost hits at negative pi, so kind of aim for that region. And then this polynomial actually follows the sine curve, goes right through the origin, you can put a dot there, follows the sine curve some more, and then right about the time it gets close to pi, it sort of escapes and goes down like that. Like we said, it was going to be one of these snakes, right? So that snake kind of hung with the sine curve for a little bit. What mathematicians, very, very smart mathematicians, discovered is that if you can write a polynomial to model a trig function, a log function, whatever function you want to model, you can plug numbers into that and get a pretty good estimation. Okay? Now, we mark the center next. The center is right there. You can see the symmetry. The center is the origin.
Okay, so the center is the origin, and the way we call centers in this chapter is with a lowercase a. A equals x coordinate what? X coordinate 0. So the center we will call a equals 0. Okay, the center you'd think it would be c. No, it's actually a in this entire chapter. All right, if you can convert sine of x into an approximate polynomial, you can then take 84 degrees, plug it in for all the x's, and get roughly what the sine of 84 degrees is. Because again, we can't really wrap our heads around what the sine of 84 is anyway, except for close to 1. Well, but you can't plug 84 into all the x's. Wouldn't that give you a pretty big number? You know what? If you remember, in integrated 3, everything is in degrees. In pre-calculus, everything is in degrees. In calculus, though, everything is in radians. We need to change this into a radian. Back in integrated 3, anybody remember flashbacks? Bring the pi in, introduce the pi, put the 180 degrees down here so that the degrees will cancel out and you can convert any degrees to radians. The degree symbols cancel. Okay, you could cross cancel. We'll just use the benefit of a modern calculator for the purposes of this class. Type in 84 times the pi button and then divide by 180 degrees. Let's see what we get. Approximately 1.466 is what I got. All right, makes sense, because remember, like the guy said on the stage, remember there was a pi over 2 is 90, that's right down the middle, and pi divided by 2 is actually about 1.571. Well, this is 1.466, a little to the left of the 90 degrees, or pi over 2. That makes sense. Now take 1.466, or the longer number from the calculator, and plug it into that x. Plug it into that x and multiply it by itself 3 times. That we can comprehend with the human brain. Multiply it by itself 5 times in a row, 7 times in a row, okay? And they'd have to get a pretty good approximation for pi back then, of course, and they could without calculators. But plug it into this polynomial, and we'll call it p sub 7 of 1.466. When you plug it into all that, you get roughly 0.99444. I've shown it to you to 5 places. Look what the sine of 84 is in actuality, thanks to our modern technology. It's 0.99452, and this was 444. Hey, not bad. You know what else we're probably going to learn today? You could probably take a guess. I bet if we added some more terms onto this polynomial, made it a little bit longer, I bet it would be even more accurate. Oh, this is interesting. Now you're starting to realize how your very calculator has been programmed. Now, looking at the second board, you can see our next topic of conversation. And I don't think high school teachers nor college professors do a good enough job of really explaining to the students what is going on here and how fascinating it is, all right? A big part of Mr. Wade's teaching, though, is not just the mathematics, but the entertainment factor. I do love to entertain. I know it's ridiculous. But what I want to show you here is that p sub 7 of x, the polynomial with all the factorials, the blue curve that modeled the polynomial, is it really like right on sine of x? Is it super glued to it, or is it like a little bit off? Well, you can see right here, p sub 7, our approximation, was a little off from the actual answer, so it must not be right on the sine curve, right? And in fact, it's not. It's close, but it's not quite there. So I did some calculations for you. The blue curve is within 0.01 of the actual y coordinates of sine of x, that close, from about negative 0.8 pi to about positive 0.8 pi. So right in there in that little range, that little window right there, okay, but not quite all the way to pi. So it's really, really super close, but that's not good enough, is it, right? We want to get closer if we can. Add more terms, right? So p sub 7 of x is only exact at one place. What about the origin? Sine goes to the origin, and also this polynomial right here goes to the origin. So where is it exact? Only at what you call the center of the polynomial. We're going to call this the center of our answer in this entire chapter, the a term. Okay? So put that up there. Only at 0, 0 is the polynomial exactly modeling sine, and that, of course, was the center. Now, I put but in capital letters right here. But p sub n of x would be exactly, wait a minute, this is crazy. A polynomial would be exactly equivalent to the entire sine curve with no error, 0 error, good word from the last chapter, if blank. And this is all the way from negative infinity to positive infinity. How could you write a polynomial that actually identically matches sine of x? If you let n, the highest power of your polynomial, approach, oh, I see where you're going, Mr. Wade, infinity. The more terms you add, the better it gets. And if you can just go to infinity or take a limit and head that way, you can get exact answers for the sine of x. Wow, that's really what's happening. Okay, and I actually used an Excel spreadsheet to run this in out to 19. So I just did 19 terms, not a big deal. What was the 19th term? Well, it ended up being a minus x to the 19th over 19 factorial. So that was the, we'll say dot, dot, dot. That was the very last term in my pattern. All right, and then what did I do? I let Excel plug in that same radians, 1.466, and I plugged it into a very long version of this polynomial all the way to that term right there. And guess what happened? It was exactly the sine of 84 through 16 decimal places. Wow. Accurate to 16 places. And if you go more, you can get more accurate results. That's pretty impressive. Now, let's talk about this. I really want you to digest this today. The actual pi, I've written the actual pi out on your page. I've written some of the important decimal places up here. But the actual pi, okay, we can use a supercomputer to do that, right? What if you get on your basic Texas Instruments calculator and you try to type in pi? Right up to there, it's accurate. After that, it goes astray, as you can see. How far is that? How many decimal places? Only 12 places. That's not so great, but I guess good enough. So the Texas Instruments is very limited, of course. All the graphing calculators, they pretty much go up to 12 places, and then they're no longer accurate for pi. Well, they use something called the Cordic algorithm. It's an acronym, actually. Capital C-O-R-D-I-C. The Cordic algorithm allows them to basically spit out things like, what's the square root of 10? What's pi? What's the sine of 84? All right. If you go to your iPhone puts pi all the way out to these zeros matching before it goes astray and it's just slightly off. Wow, that's pretty impressive. So how many places are accurate on your iPhone? It's actually 32 places, and pretty much the same for all smartphones. They'll go all the way out to 32 places, all right? Very, very nice. Now, what do they use? They're apparently not using the Cordic system because that one's pretty limited, right? Well, guess what? The iPhone uses a program written by Steve Jobs, the founder of Apple, who came up with the iPhone. Okay, rest his soul, of course, he's passed on now. You thought he was just a very sharp businessman? No, he's a genius. He's a mathematical genius. So he wrote this program that's still used today in the iPhone that goes all the way out there correctly. All right, so we'll say Steve Jobs program because the guy was incredible. There's a reason he was one of the most successful people in the entire world, all right? No accident. All right, so then we go to a computer. Just pull out your standard laptop and use the calculator on your laptop and put in pi. Guess what? Far more accurate, 46 places. Wow, that's very accurate. That's 8 places past the end of the screen here, all right? So very accurate. How? How is your basic laptop calculator so much more sophisticated than the iPhone and way more sophisticated than the Texas Instruments? Well, they use something called Taylor Polynomials. And guess what we're studying in this chapter? How to write your own Taylor polynomial for maximum accuracy. And of course, we'll also write these as Taylor series. Oh, that's why we learned series in the last chapter. We're going to write some more of our own series this time. Interesting, all right? Polynomials and series. And what's a series? Just a pattern. And what does that look like right there to you? It's a pattern, right? Clearly. This stuff is so fascinating, it deserves its own history break, which we haven't done in a while. Let's do a very quick history break to see how did mathematicians even figure out how to model sine, cosine, tangent, natural log, regular log, square root, cube root, fourth root with a simple polynomial. Let's find out. 1668, the book Logarithmotechnia was published by Nicholas Mercator, revealing three major mathematical discoveries. Number one, functions first written as polynomials, the foundations of programming modern calculators. Number two, a special type of logarithm was debuted in this book, known as natural log. And number three, the area under the hyperbola y equals 1 over x was found to be the natural log of the absolute value of x. In 1715, the primitive method for writing functions as polynomials was published by number 135, Brooke Taylor. In 1748, the modern method of writing functions as polynomials was published by none other than number 1, Leonard Euler. How, Mr. Wade? How do I write my own polynomial to model sine, cosine, natural log? How do I do it? Let me show you right here. And it's mandatory in BC Calculus and in Calc 2 in college. So we might as well anyway and have some fun with it. All right, write the first three non-zero terms. Sometimes you'll get a term that is 0, and so you just leave that out. Of the Taylor polynomial, named after Brooke Taylor, those polynomials from the front page. And we're going to model f of x equals sine of x, the same thing I modeled on the front page. Now, what's this about x equals 0? That's the center. Remember, it was centered at the origin? Okay. When they say about x equals 0, they mean that a equals 0. All right, that's what we call the center. And you can shift the center. If you want to do sine values for a little bit farther down the graph, you can shift the center and get good accuracy down there. All right, step number 1. The secret of writing your own polynomial to model any function on the planet. And you can do any function with this. Derivatives. This is related to derivatives. So first, take the sine of x, all right? Our original function, f of x is sine of x. You always start with the original function. All right, next box, f prime of x. F prime of x is cosine of x times the chain rule of 1. So that's the first derivative, derivative number 1. This is sometimes referred to as the 0th derivative, the original function. So that's derivative number 0, but you do have to start with the original. F double prime of x. The derivative of cosine becomes negative sine of x times chain rule 1. The third derivative, the triple derivative of sine of x. Derivative of negative sine is negative cosine of x times the chain rule of 1, as we all know. Now, if you remember way back when we studied this, like August, September, a long time ago, the fourth derivative, that's where you start putting a little number inside of parentheses instead of putting all those prime marks, all right? And you also put it in parentheses so it doesn't look like an exponent. The fourth derivative, the derivative of negative cosine, is positive sine. Not all derivatives return to where they came from, but sine and cosine do, all right? And then, doesn't really have anything to do with today, but it's interesting. The fifth derivative, the derivative of sine is cosine, chain rule 1. We'll take it that far, okay? We'll go that far today. Now, step number 2. What is the next secret, all right? Plug in the center. A equals 0 in this case because we want to center it around x equals 0 to model the front page, all right? Plug in the center. So, f of 0 is the sine of 0. Now we can handle that, okay? They knew the sine of 0 back then. The sine of 0 is 0 because it goes to the origin. That much they knew. F prime of 0 is the cosine of 0, which is a peak, which is 1. F double prime of 0 is negative sine of 0, which is 0. The third derivative of 0 is negative cosine of 0, which is negative peak, so it's negative 1, just the negative of this one. Of course, it will be no surprise that the fourth derivative of 0, since it's another sine, will be 0 again. Remember we said something about skipping the 0 terms and sticking with the non-zero terms? Okay, that's coming in here. And then the fifth derivative. Oh, oops, let me put the 0 first. The fifth derivative is going to be cosine of 0, which is 1, and now we start to establish a very nice pattern. 0, 1, 0, negative 1, 0, 1. Kind of like the oscillators in chapter 11. So finally, step 3. Now here's the genius of the number 1 ranked mathematician, Leonhard Euler, right here. He figured out that if you do the nth derivative and you plug in the center that we call a, and you put that over n factorial, and you multiply that on the side by x minus the center to the nth power, that formula will create a polynomial that models all these functions very well. Euler, just out there on a different planet, let me tell you what. Take the nth derivative and plug in the center. That's what we did. This whole column has got us covered right here. Okay? What is the 0th derivative at the center? It's 0. That's going to go on top of your fraction. Let's just do the tops. It's way easier for your brain to focus on one thing and not jump all over the place here. So the first derivative at the center was 1. Okay? N equals 2. The second derivative at the center was 0. The third derivative was negative 1. The fourth derivative was 0, and the fifth derivative was 1. And that pattern continues to infinity, of course. Now on the bottom, we're going to put n factorial. Okay? This was, let's see, n was 0, so we're going to put 0 factorial. N was 1, we're going to put 1 factorial. N was 2, we're going to put 2 factorial. It's starting to create the pattern on the front page, by the way. N equals 3, 3 factorial, 4 factorial, 5 factorial, to infinity. All right? And then on the side or top, I like mine on the side, we're going to have x minus the center, so it controls the shift, right, left, shift. That's integrated 3. Never did you think you'd see it this way, though. X minus the center to the what power? To the nth power. Well, right now we're on step 0, so it's to the 0th power. Okay? X minus center, 0, to the first power. X minus 0 to the second power. So you just keep doing x minus center all the way down to the third, x minus 0 to the fourth, x minus 0 to the fifth. And you put all that together and you can make your own Taylor polynomial. Right up to the side, you can kind of simplify this a little bit. I have to use another board, but I probably like to simplify and then put it all together. So, okay, 0 over anything is 0. Now, you may want to remember this. 0 factorial is 1. That is not 0, okay? 0 factorial by definition is 1. There's lots of ways to prove that. That'll be a different discussion for a different day if you've never seen it before. So that's not 0 over 0 because that would be indeterminate. It's 0 over 1, which is 0, so the whole first term's gone, okay? The third term is 0 over 2 factorial. That's 0. Wipes out everybody. The fifth term is 0, okay? So the first, and the third, and the fifth terms. Now, the other ones. 1 over 1 is 1. X to the first is x. Okay, that's going to be our first term right there. Negative 1 over 3 factorial is 3 times 2 times 1, which is 6. Negative 1/6 x cubed. Drop the 0. And then the fifth term, all right? Actually, technically it's the 6th term. Sorry, it's n equals 5, but 6th term. So 5 times 4 times 3 times 2 times 1 is 120. So it's 1 over 120. X drop the 0 to the fifth. And now we can write an official polynomial at the very bottom. You've got space. Again, I don't. So your polynomial, the first 3 non-zero terms, this one, that one, and that one. And we're going to add them all together, just like a series. Very close connection to series in this chapter. Just like a polynomial, all right? So we'll call it capital P for polynomial. We'll call it P of x. And we will write the first term, which is 1x, plus negative 1/6. So plus minus means subtraction. Minus 1/6 x to the third. And then finally plus 1 over 120 x to the fifth. And by the way, what was the highest power we came up with? 5. So we call it P sub 5. Okay? That's called a 5th degree Taylor polynomial is what that is right there. And there is your official polynomial. Very interesting. Now on the front page, we left it in factorial form. I wanted you to see that very nice pattern. You wouldn't have appreciated it here. Here I just went ahead and multiplied it out. A lot of times we'll probably just leave the factorial. Sometimes we'll multiply it out. We'll probably just leave it most of the time. But I just wanted you to see it. So that will give you sine values as long as you stay in a relatively close area and don't escape that area where you remember where it just went completely different, right? Diverged, right? Okay, there's your answer.